In previous videos, we have discussed the joint distribution and conditional distribution and various related concepts for two random variables. Oftentimes, we have to deal with more than two random variables. So today, we're gonna extend what we have discussed so far into the case where there are more than two random variables. First, the concept of joint distribution for more than two random variables. Let's consider an integer k and k number of random variables denoted by x1, x2 to xk. The joint distribution of these k random variables can be written as this: f subscript x1, x2 to xk evaluated at the realization of each of these random variables, little x1, little x2 to little xk. And that probability mass function equals the probability that x1 variable equals little x1 value, x2 variable equals little x2 value, and xk variable equals little xk value. And below is an example of the distribution of three random variables. This is a generalization of an example we considered before. Here there are three variables, x1, x2, and x3. x1 stands for vote. x1 equals 1 if vote is for Biden in the general election, and 0 for Trump. And x2 is the gender variable that equals 1 if the person is male, and it's 0 if the person under consideration is female. And x3 is a race variable that takes the value 1 if the person is white and is 0 if the person is non-white. Obviously, the two-way table is not enough to describe the joint distribution of three random variables. Well, because our x3 or all the x variables are only binary variables, meaning that they take only two values, we can use two-way tables to represent the joint distribution. So the two tables are labeled by the value of x3. So the first table describes the joint probabilities associated with x3 equals 0, and the second table describes the joint probability associated with x3 equals 1. And then each table has 4 cells, and these 4 cells represents the probability corresponding to the 4 pairs of values for x1 and x2. For example, 0.01 is the probability of x1 equals 0, x2 equals 0, and x3 equals 0. And similarly, this 0.25 cell is the joint probability of x1 equals 0, x2 equals 1, and x3 equals 1. So that's how you might describe the joint probability mass function for three random variables. When you have three random variables, the conditional distribution can be somewhat more complicated. Conditional distribution can be, for example, the conditional distribution of x1 given x2 and x3. Like, can be the conditional distribution of one variable given two other variables. And that again follows from the conditional distribution formula. That's a ratio of the joint distribution of the three random variables and the marginal of the conditioning random variables. Or you could have a different conditional distribution. You could be considering the conditional distribution of x1 and x2 given x3. Now the conditioning variable is x3, and we are describing the distribution of x1 and x2. So that also equals a ratio where on the top is the joint distribution of all three random variables. And that is divided by the marginal distribution of the conditioning random variable, which is x3 now. And what is the marginal distribution? The marginal distribution, for example, of x2 and x3 is obtained by summing up the joint distribution over x1 and the marginal of x3 is obtained in the same manner, but we just sum over, sorry, this is a function of only x3. We just sum over little x1 and little x2. All right, so these are the conditional distribution and marginal distributions that can be generated from a joint distribution of three random variables. Obviously, with more complicated notation, you can define these quantities in the case where there are more than three random variables. What about expectations of a function of three random variables? Here we consider a function g of three arguments, x1, x2, x3. What is the expectation of g of x1, x2, x3, where these x1, x2, x3s are the random variables, the capital letters? Expectation of this, in the same principle as we defined all expectations, this expectation is a weighted average over all the possible values of the argument for the g function, all the possible values of the random variables x1, x2, and x3. We sum them up. We sum up or average up the values of g evaluated at these values of x, and we use the weight that's given by the joint probability mass function of the three random variables. For example, in the joint distribution described by this two-way table, we can calculate, for example, the product of the three random variables, the expectation of the product of the three random variables. The product of these three random variables can be either 0 or 1. In fact, it's almost always 0, except in one case when all three variables are 1s, and where the joint PMM is 0.15. Therefore, this expectation should be 0.5 times 1, which is 0.15. With conditional distribution, we can also define conditional expectations of random variables in the context of more than 2 random variables. For example, we can define the conditional expectation of x1 given x2 equals little x2 and x3 equals little x3, and that using the principle for any kind of expectations, this is an average over the x1 value with the weight given by the conditional PMF of x1 given x2 and x3. Clearly, this is a function of little x2 and little x3. We could call that function g of x2 and x3. So if I write 3 horizontal slashes, that means we define g to be this value, to be this function. We define g of x2, x3 to be this, because this is a function of x2 and x3. We can call that function g. Then if we evaluate g at the random variables x2 and x3, then g of random variables x2 and x3 is also a random variable. And that random variable can be denoted ex1 given x2, x3. And that's how we view conditional expectation as a random variable. So once we have this conditional expectation formula, we can calculate other conditional expectations as well. For example, what is the conditional expectation of g of x1, x2, x3? And I was using g for a different notation. Let's maybe call this g a m function. What's the expectation of m x1, x2, x3? M is a function of these 3 arguments, conditional on x2 and x3. How do we find this conditional expectation? Well, first realize that given x2 and x3, these arguments x2 and x3 are fixed. So what we are averaging over is only x1. So we only need to use the conditional distribution of x1 given x2 and x3. So that should be an average over x1, m of little x1, capital X2, and capital X3 times the conditional distribution of x1 given x2, x3, little x1 given x2, x3. Okay, so let me explain a little bit the notation. I should have explained earlier. So when you write the subscript of a probability mass function, we always use the capital letters because the subscript tells us what this PMF is for. So this PMF is the conditional PMF of the x1 random variable given the values of the x2 and x3 random variables. Well, in the argument of the function, here because we are evaluating the PMF at the little x1 value, which we are summing over, so this should be the little x1 value realization of x1. Well, we are conditioning on x2 and x3, but we are not given the realization, the specific realization of these 2 random variables in this particular problem. So we use the capital letters x2 and x3. Now, remember, we had this law of iterated expectation when discussing the distribution of two random variables. When we are considering more than two random variables, there is another law of iterated expectation. We may call it the law of iterated conditional expectation. What the law of iterated conditional expectation says is something like this. So when you take conditional expectation given x2 of another conditional expectation given x2 and x3, that will be the same as just taking one conditional expectation given the conditioning variable of the outer expectation. So remember, expectation is an average, and conditional expectation is like average within a group defined by the value of the conditioning variables. So the inside conditional expectation on the left-hand side is within group mean, within group average for a group defined by both x2 and x3. That's a more finely defined group. Say, suppose x2 is gender, x3 is race, then this conditional expectation is the conditional expectation for a group defined by race and gender, say for the female white group and for the female non-white group, and for the male white group and female white non-white group. So this conditional expectation is conditioning on finer information. Well, this outer expectation is conditioning on cruder information, because the outer information, outer conditioning variable only provides the information about one variable. Well, the inner conditional expectation provides information, is taken given the information on two random variables. So this is finer information for the inner conditional expectation and cruder information for the outer conditional expectation. So, and this is crucial for understanding the law of iterated conditional expectation, finer information. Cruder information. So why am I talking about information here? Remember, at the very beginning of the discussion of conditional expectation, we said that conditional expectation, at the very beginning of the discussion of conditional distribution, we said that conditional distribution is the revised distribution after the realization of the conditioning variable. Or the realization of the conditioning variable provides us with information. Given that new information, we revise the distribution of the variable of interest. In this case, that's x1. So the more conditioning variable there are, the more information is reviewed, because the realization of two random variables are known. And that is more information than where only the information about one variable is reviewed. And this iterated conditional expectation will equal the conditional expectation given only the cruder information. So why is this true? We can do a brief proof of that, just using the definition of conditional expectations. Let's write out the outer expectation first. As you see, this conditional expectation is actually a function of x2 and x3, right? It's a function of x2 and x3. Now, x2 is given when you're taking the outer expectation. The only thing we're averaging over is x3. So that when you write out the outer conditional expectation, you get sum over x3, the little x3 realizations. We are summing over all the possible realizations of the random variable x3. We sum over x1, x2, and x3 equals little x3, with the weight that's given by x3 conditional on x2 evaluated at little x3 conditional on the x2 random variable, because we're not given, because we are not specifying which realization x2 is equal to. Next, we are going to write out this conditional expectation as well. And that clearly is averaging over x1, because we're taking an average of x1 given x2 and x3. So we sum over x1, in the conditional distribution of x1, x2, x3, x1, x2, x3, and that conditional distribution is the joint distribution divided by the marginal of x2 and x3 times this this conditional distribution of x3 given x2, which can also be written as a ratio. That's x2 and x3 divided by the marginal of the conditioning variable, which is x2, evaluated at the random variable x2. So this conditional expectation is written as this ratio. Well, this ratio is the conditional expectation of x1 given x2, x3. Now that we have written everything out, we can realize that this x2, x3 marginal distribution can be canceled out. So that is canceled out. So we are left with sum over x3, sum over x1, joint distribution of x1, x2, x3, divided by marginal distribution of only x2. Now we can exchange the order of summation, and that gives us sum of x1 and x1 times sum over x3, the joint distribution of x1, x2, x3, divided by the marginal of x2. But what is this sum of the joint distribution over x3? We are summing over x3, so that becomes the marginal distribution of x1, x2. So we have, that is sum over x1, little x1, joint distribution of x1, x2, evaluated at little x1, big x2, divided by the marginal of x2. And what is this ratio? This ratio is the conditional distribution of x1 given x2. Therefore, this weighted average is conditional expectation of x1 given x2. So that proves the law of iterated conditional expectation. So I want to reiterate that there should be an inclusion relationship between the conditioning variable for the inner conditional expectation and the conditioning variable for the outer conditioning expectation. The conditioning variable for the outer expectation, that's x2, should be a subset of the conditioning variable for the inner expectation. So there should be fewer random variables here on the outer and more here. Fewer random variable means cruder information. We know less when we're calculating this outer conditional expectation. Well, the inner has finer information. And that is very important. And to demonstrate why that is important, let's consider two expressions that look like iterated conditional expectation, but really it's not. Now let's look at the first expression. In the first expression, we're taking two conditional expectations, obviously, but the outer conditional expectation has more conditioning variables than the inner. What does this expression equal to? Does it equal E of x1 given x2, x3? Well, it doesn't. What it equals to is quite clear. And without any calculation, we can figure that out. Why so? Because first, we can realize this conditional expectation in the inside is a function of x2. This is a deterministic function of x2 and nothing else. It's a function of x2. So if it is a function of x2, then given x2 and x3, the value of this function is already given. It's non-random. So therefore, the conditional expectation of it is itself. This is simply because this is a function of x2, and x2 is part of the conditioning variable for this outer expectation. And the next one, the next expression is a little bit trickier. In the next expression, we're taking conditional expectation given x3 on the outside, and on the inside, we have a conditional expectation of x1 given x2. What is this? Well, we can write out the outer expectation using the conditional expectation formula. So the inner random variable, so the inner conditional expectation is a function of x2. So we are averaging over x2. For all the values of that random variable evaluated at little x2, using the weight conditional distribution of x2 given x3. These actually, it does not in general equal conditional expectation of x1 given x3. It does not equal. This is because the inner expectation doesn't have finer information than the outer expectation. So what is EX1 given X3? That is sum over X1 of X1 given X3, X1 given X3. And that is not the same as this expression. Well, you can verify that by also writing out this conditional expectation. You find that nothing cancels out to give you this simple expression. So these two are not equal. So some beginners of probability may make the mistake of applying law of iterated expectation on something like this, but that's not correct. You have to make sure that when you apply law of iterated expectation, you have to make sure that the inside conditioning random variable has to be has to contain more variables than the outer expectation. Here is an example where we illustrate the law of iterated conditional expectation. The example is taken from the example we gave at the beginning of the video. So this is the joint probability mass function or joint distribution of three random variables, x1, x2, and x3. And we have calculated their conditional expectations of x1 given each of these four pairs of values for x2 and x3. Now we calculate them to be 3/8, 3/5, 9/10, and 3/4. You can verify whether these calculations are correct or not using the conditional expectation formula. Now let's suppose these are correct. We can write conditional expectation of x1 given x2, x3. This is a function of x2 and x3. We can write them in this table. This random variable can take four possible values, each with the following probabilities, which is also implied by this three-way table. And each of the value for ex1 given x2 and x3 correspond to a pair of values for x2 and x3. Okay. So this table describes how this random variable is related to x2 and x3. Now we can calculate, we want to calculate the conditional expectation of this random variable given only x2. x2 has two values, so we calculate the value of the realization of those two. We calculate the conditional expectation at these two values separately. Consider x2 equals 0 first. For x2 equals 0, we have two cases for ex1 given x2 and x3. It's in this circle. There are two values, 3/8 and 3/5. And their relative probability is given by this relative probability of 0.4 and 0.1. So we have 3/8 times 0.4 divided by 0.5. 0.5 is the marginal probability for x2 equals 0. Plus 3/5 times 0.1 divided by 0.5. So that's so we can cancel this out. That's 2. Therefore, that's 3/10 plus 3/25. And that is 50 on the bottom, and on top is 15 plus 6, 21. And we can do the same thing for the case where x2 equals 1. Now we need to consider this, the probability and the values in this square. In this case, the random variable ex1 given x2, x3 has two values, 9/10 and 3/4, and their relative probabilities are given by the relative magnitude of 0.1 and 0.4. So that should be 9/10 times 0.1 divided by 0.5 plus 3/4 times 0.4 divided by 0.5. So that's like 9/50 plus 30/50. So that's 39 divided by 50. So this is calculating the left-hand side of the law of iterated conditional expectation. To calculate the right-hand side, that is, to calculate expected value of x1 given x2 equals 0, and conditional expectation of x1 given x2 equals 1. We just need to figure out the marginal distribution of x1 and x2, which can be described in a two-way table. So for x1, x2 equals 0, the probability is the sum of these two values. So that's 0.29. And for 0, 1, that's 0.11. And for 1, 0, that's 0.21. And for 1, 1 is 0.31. So E of x1 given x2 equals 0 uses the first column. So that should be 0.21 times 1 divided by the marginal of x2, which is the sum of the first column, which is 0.5. And that is 21/50. Similarly, using the second column, we can calculate the conditional expectation of x1 given x2 equals 1. So that should be 0.39 times 1 plus 0.11 times 0, which should just be 0.39, and then divided by the marginal of x2 at 1. So it's the sum of these two numbers, which is also 0.5. Okay, so you get 0.39 divided by 0.5 is 39 divided by 50. So as you can see, the left-hand side and the right-hand side are equal for the law of conditional iterated expectation, or law of iterated conditional expectation. The last thing I want to talk about in this video is the independence of multiple random variables. As we said before, the independence of two random variables is defined by the fact that the joint distribution satisfies the product rule. And the definition of independence for more than two random variables is the same. So x1, x2 to xk are independent or statistically independent or jointly independent if the joint PMF of the k variables is the product of the marginal PMFs. Satisfies the product rule. Well, I want to stress that this joint independence of k random variables is stronger than pairwise independence of these variables. So what's pairwise independence? Pairwise independence is that each pair chosen from these k random variables is independent within the pair. So for any index I and index j, this pair of random variables xi and xj satisfies the product rule. For any I not equal to j, I and j are chosen from 1 to 2k. So this is pairwise independence. And that is a weaker concept than the joint independence. The joint independence implies the pairwise independence, but the opposite direction doesn't hold. This is no surprising to us because we have talked about joint independence of multiple events in maybe the first week's videos. The joint independence of more than 2 events is stronger than pairwise independence of the events. And there we give an example of 3 lights. The 3 lights are in 3 closed door rooms. They could be on or off. If they are on, it's denoted 1, and off is 0. Then there are 8 states of the world depending on their on and off status. So there are 8 states of the world, and the distribution on these states of the world we consider is given by this. Suppose that distribution is given by this PS function. And we can define the x variable, y variable, z variable to be 1, 0 variables, and x equals 1 if the first light bulb is on. So it's 1 when the state of the world is these 4. And y, similarly, y is 1 if the second light bulb is on and is 0 otherwise. And z is 1 if the third light bulb is on and 0 otherwise. These 3 random variables are pairwise independent. So probability that x equals 1, y equal 1, z equal 1 equals probability of 1, 1, 1, right? So that equals 0 given by the table. And probability that x equals 1 probability that x equals 1 is the sum of these 4 states, right? So it's 0, 0.25, 0.25, and 0. So that's 0.5. Probability of y equals 1 is the same, calculated the same way. Probability of z equals 1, you can verify, is also the same, 0.5. Clearly, these 3 are not jointly independent. So because this joint probability of x, y, and z is not equal to the product of the 3 marginals. So not x and y and z are not independent, are not an independent group of variables. But pairwise, they are independent. You see, probability that x equals 1 and y equal 1, which is the sum of this event and this event. And that's 0.25. And you can calculate the same thing for y equals 1 and z equals 1, as well as x equals 1 and z equals 1. They are all 0.25. And they do this pairwise joint probabilities do satisfy the product rule. And you can verify this for all combinations of the values. You can replace the 1 by 0, 1 by 0, or both 1s by 0s. You can verify that the product rule is always satisfied pairwise for these three random variables. So x and y and z are pairwise independent. The last point I want to make is that if the group of random variables x1, x2 to xk are independent, they're jointly independent, then any function of a subset, let's say the first m of these random variables, and any other function of the rest of the random variables are independent. So the key for these transformations to be independent is for the two transformations to use disjoint sets of random variables. As long as they use disjoint sets of random variables from this independent group, these two transformations are independent from each other.